Well, good morning, everybody. My name is Deb Beatty. I'm the Area 3 Director, and I'm here to welcome you to our annual Amelia Earhart Fellowship presentation. We're so glad that you're all here. I'd like to make a few introductions before we get started. First of all, I want to thank the Zonta Foothills Club of Boulder County and their president, Catherine Nadal. They're the host club for this year's Area 3 meeting and the Amelia Earhart Foundation. Goodness. Could I please get anybody who's not talking to mute, please? Could you mute your computers if you're not speaking? That would be wonderful. Thank you. Thank you to our host club, Catherine Nadal, their wonderful president. Thank you so much for all you do. Thank you for Michelle Nadal, who is doing the IT portion of this presentation. If it wasn't for Michelle, we all wouldn't be here because I certainly couldn't do it. I want to introduce former governors who are on our call today. We have several former governors joining us today. The former governors we have are Renee Kopic, Mary Benoit. Is Sheila on? No, Sheila Davis, if she's on, she's a former governor. Marcy O'Toole and Kay Meyer. I also want to introduce our current governor, Ann Hodgson. She'll be speaking to us just a few minutes about the Amelia Earhart Fellowship in the background. And with that, we'll take it away.
Okay, so Michelle, go to the next slide.
Marcy, it's up to you.
Yep. Oh. All right, so sorry, back up. And then I will introduce the fellows. Sorry. I thought you were going through the whole agenda. I'll introduce the fellows, and then both Yashika and Jamie will be doing their presentations. We will do the presentation virtually of your certificates and your wings, and then we'll do closing. So with that, I'd like to introduce Ann Hodgson, our current governor for District 12, to give a little bit of background about the Amelia Earhart Fellowship.
Hi, and welcome everyone. This is always a very exciting meeting to attend, and we're glad so many of you were able to come. I was asked to talk about the local slant of Amelia Earhart. And the first thing I need to say is that CU obviously has an exceptional aerospace program. Since I joined Zonta about 16 years ago, I think there was 1 year, I know it wasn't more than 1 year, I think there was maybe one, that there was no fellow from CU, and that's an amazing record. 1 year there were 6 fellows, and we could just not hardly even believe that. That was the year that Sharon Langenbeck, who was then the Zonta International Amelia Earhart chair, joined us for the ceremony, out on her own dollar because she was just so excited about it. Sharon herself was a 2-time Amelia Earhart fellow back when they used to be able to apply twice. I want to give a nod to Penny Axelrad, who has been the chair of the space department at CU. She's a great supporter of the fellowship and has given several presentations as part of our Amelia Earhart luncheons over the years. And another shout out to our District 12 clubs for their support of the fellowship program with contributions to the Zonta Foundation for Women. And I'll turn it back over to Marcy.
Okay. Thank you, Ann. Next slide, please, Michelle. I am pleased to announce our 2 AE fellows, Yashika Khatri from India. She's attending CU, as well as Jamie Voros, and her citizenship is Australia and United Kingdom. So at this point in time, I'm going to introduce the fellows, and then the fellows are going to be doing the presentation. So next slide. Okay. Yashika is in the Aerospace Engineering Sciences of University of Colorado Boulder. Her study is modeling the dynamical uncertainty of objects in space. She's a mentor in the aerospace Outreach Programs, has been appointed Senator for the College of Engineering and Applied Sciences in CU Graduate Student Government. She's also Professional Development Chair in Aerospace Department Graduate Student Organization. And she enjoys reading, painting, traveling, and she recently added in boxing and learning Italian. One sec, sorry. She's also supportive of STEM in US and India. And her title of her presentation today is the Nonlinear Uncertainty Propagation for the Conjunction Analysis. And with an increasing number of space objects, close proximity situations between these objects occur every day. This makes tracking these objects and computing their collision probabilities is absolutely essential. Her PhD project aims to find fast and accurate methods to compute chances of collisions between objects in space. And with that, I'd like to turn it over to Yashika.
Thank you so much for the kind introduction, Marcy. I'm just going to share my screen here. So first of all, I just want to thank Zonta and all of you, because without this, I wouldn't have this fellowship and this opportunity. And I'm going to start with my presentation. Hopefully, I'll try to keep it, I'll try to explain it well. So hopefully you'll understand what's going on. I'm a student in the Celestial and Space Flight Mechanics Laboratory at CU Boulder under Dr. Daniel Shears. And today I'm presenting the topic Nonlinear Uncertainty Propagation for Conjunction Analysis. As we go through our motivation, I'll explain what this means kind of piece by piece. So I'll start with the research motivation. So why I do this research. I'll go over our method, our solution to this research, and then I will go over some case studies at the end, just to show that our method works. So where does the motivation for this research come from? The main reason is there's more than 27,000 objects in space that have been cataloged that are greater than 10 centimeter in diameter. And there's more being launched to space every day, and there's more debris being created every day. A large number of this debris comes from collisions in space. When two objects collide in space, lots of fragments go off of that explosion, and that just increases our number of debris in space. And this can be really harmful to any space missions we have, any GPS satellites we have up in space, and any other launches that we have in the future. This is going to be troublesome. So the US Space Surveillance Network actually monitors and informs on any close encounters between two of these objects that happen in space. So each observed object in space, you can see a little satellite image here, has a state associated with it, which tells us where it is and how fast it's going. And it has an uncertainty associated with it. So we can say within 90% confidence, let's say, that this satellite is here. That means that it could be in this ellipse region. It could be anywhere in this region, but we're 90% confident that it's in this middle stage. So we call this the mean and the uncertainty of an object. So all the current methods of propagating this object forward in space involve numerical integration. And that's why our research becomes important. Numerical integration, although great, is very computationally expensive. So you can kind of see an image here of how the propagated object would look without this uncertainty associated with it. So if you just propagated this satellite forward, it would follow an orbit in space, and it would end up at this different state at time 2. Now, if we bring in its uncertainties, saying that we're 90% confidence in its state, that 90% confidence interval, that uncertainty changes into this crescent-shaped uncertainty in the future. And the reason that happens is because we use nonlinear dynamics in propagation, and all dynamics in space are generally more nonlinear. So how do we perform this propagation every day? So how is it happening in industry now? That's through numerical propagation and Monte Carlo analysis. So what we do is this uncertainty in the beginning, saying that we're 90% confidence, this is where the satellite is. Excuse me. Within this uncertainty, we take millions of points, and we propagate these individual points forward to a future time. At this point, all of these points together give us this new crescent shape. And this is a very accurate method. This always gives us our crescent shape in the future and always tells us where our satellite is going to be in the future. But the problem is it takes a lot of time and resources to perform this integration. This is why we try to find our analytical methods. Now I'll talk a little bit about probability of collision, which is the same as conjunction analysis, which was the second part of the title of the presentation today. So why is this applicable in our work? So even if two satellites propagated forward don't exactly intersect with each other, if their uncertainties intersect with each other, that means that there's still a chance that they could be in collision space with each other. And that's what we call probability of collision. And that is the chance of these two satellites colliding based on their uncertainty and their positions. And this is kind of what it looks like in space. If you propagate two objects forward and you have these overlapping crescent shapes, that means that there's a chance that a collision could occur. Now, if these two crescent shapes were far away from each other, we would say that there is no probability of collision, so our probability would be 0. And if these completely overlap and the two satellites are in the exact same space, you can say the probability is 1. If you 100% know where the satellites are and they overlap, so essentially probability of collision ranges from a 0 to a 1. And it changes based on the overlap here, how much of an overlap you have between the two spaces. And if this conjunction probability or collision probability is high enough, that's when today in industry, we move our satellites out of the way. We make maneuvers so that we don't go through any collisions or even conjunctions where the two satellites come close to each other. ISS makes maneuvers very often to avoid any pieces of debris coming towards it. So this is our research motivation, that numerical propagation takes a very long time. So our Monte Carlo method is very high in computational expense, even though it's very highly accurate. That's why we find these analytical and semi-analytical methods that don't involve numerical propagation, because the computational expense is very low. Some of these methods are thousands of times faster than our Monte Carlo methods. And depending on the method, we can get very accurate results with this as well. So this is the main motivation, is to find our fast and accurate analytical and semi-analytical methods to this problem. On the right, you can again see this initial uncertainty distribution that we have been talking about, and it propagated forward to this crescent shape in the future. I hope that the name of our presentation is a little more clear now, because we are propagating our uncertainty into the future and performing conjunction analysis with it, so that we can see what the probability of collision between two objects becomes in space. So that's the title of our presentation today. I just brought it back up to see if everybody has a good understanding of this. So we'll go over our analytical method now. And this involves a couple of mathematical tools, which is Gaussian mixture models and state transition tensors, and we'll go briefly over what they mean. This section is a little more technical, but I hope I can explain it well to you guys. So going over the basics, what are our main goals today with our method? It is to propagate our state and uncertainty forward, fast and accurate, and to calculate our future probability of collision with different objects. So the mathematical tools we use here are, we split this uncertainty, this initial ellipse, into smaller distributions. We do these because smaller distributions preserve their linearity for a longer time. So if we propagate individual little pieces of this forward, then it would be a more accurate propagation than propagating the whole distribution forward. So that's why we use our Gaussian mixture models. Then this individual pieces split up in this initial uncertainty are propagated forward using our state transition tensors, which are STTs. So this is our general method. We start with our Cartesian state, which means we are looking at objects in an XYZ space. In space, so we can visualize them well. We switch that into a different coordinate frame to reduce dimensionality. We perform this GMM splitting so that the uncertainty is split into little components. We perform propagation of the individual components. We propagate it, we switch it back to our Cartesian space after propagation. and we calculate our final probability of collision. So that's our general method, and I'll be going over this pretty quickly today. So starting with our initial distribution, once we have it in our desired orbital frame, we perform the GMM splitting. How does that work? If you remember this initial uncertainty of an ellipse that you saw at time 1, and this is the mean or the estimated position of our satellite, this is how you can split this total uncertainty into the little uncertainties. And this total PDF just becomes a sum of these individual little uncertainties, but just weighted. So that's how we get our total uncertainty here, is that it's a weighted sum. This whole uncertainty is a weighted sum of these individual uncertainties, and each uncertainty has this ellipse and this mean associated with it, as we already saw here with this ellipse and the satellite in the middle. So now how do we go from this initial ellipse that we saw to this final crescent shape? And the way we do that is, again, by propagating these individual small components forward so that we can propagate them more accurately, and then taking the sum of this initial distribution to get our initial distribution, and taking the sum of these final propagated little components to get our final crescent shape. Now, how do we perform this individual propagation? That's through state transition tensors. And you can see a little image of one object being propagated here. So we're talking about these individual objects being propagated forward in time. I wouldn't go over the equations, but this is how we represent our state transition tensors. They're essentially higher order, including higher order terms. They're essentially equations that help us propagate deviation forward in time. Now, how do we use these SCTs to propagate our little components forward? It's using these two sets of equations, one that help us propagate these plus signs or our means of our little distribution, and then the second equation that helps us propagate these ellipses forward in time. This is what an example of this looks like in real data. So you can see the little yellow points in the middle that represent our Monte Carlo analysis. That's the numerically propagated portion of our truth. And then these little blue ellipses here and the plus signs, as you can see, they capture our Monte Carlo points completely in this weird crescent shape. And that's our goal with this analytical method, is that we produce these ellipses and these pluses that together added up cover our Monte Carlo analysis points.
And I put that.
So once we have this propagation done, we can switch that back to our Cartesian space to calculate our probability of collision.
What?
And then we go into our conjunction analysis or probability of collision calculations. Again, if you remember this image from before, we have these initial ellipse uncertainties associated with the two satellites. We propagate them forward, and there's an overlap in this future crescent shapes, and that's where we get our probability of collision. So now we have our truth, which is our numerical propagation, which is the industry standard today. How do we compute that? As you can see, this is the overlap we saw. Whenever there are 2 points closer to each other, then the combined radii of the two objects, we consider that to be a collision. And this is done with millions of points. So the number of collisions you have over the total number of Monte Carlo points you have gives you what your probability of collision would be, which should be easier to understand. The GMM STT model is a little different, where we have these analytically propagated little portions of our final uncertainty. The overlap of these objects is what gives us our probability of collision in our method. So this is just the difference. On the right images, I think it clarifies the difference between the two, where in the top one, we take points in these final uncertainties. And in the second one, we take these little uncertainties within this large uncertainties at the final time. So that's our method. We finally have our probability of collision. Now for verification, we just look at one case study today. And this is in basic two-body problem dynamics, which means we just have Earth and our satellite, and that those are the only two things interacting. Those are the easiest dynamics you can use in space to propagate objects forward. So on the left, you can see our two initial objects, just like you saw before, our little ellipses with the two satellites in the middle. you can see what their orbits around Earth will look like. You can imagine a little Earth here in the middle of these orbits. On the top right, you can see how they look propagated, which was the crescent shapes we saw before at time 2. And this is what the plot of these points propagated forward in Monte Carlo analysis look like, which is these little dots. The yellow one is associated with this first object. These blue dots are associated with the second crescent shape. And if we overlap these crescents on top of these distributions, we hope to see a complete capture like we saw in the example before. On the bottom right, you can see our final results, where this blue solid line in the middle is our Monte Carlo probability of collision. The dashed lines are our 95% confidence interval bounds. And you can see that as we approach a large number of Gaussian mixtures, in this case 200, which means that we're splitting up this final uncertainty into 200 little pieces and then propagating it forward. So at 200, we have our convergence around 200. So you can see that it finally converges with our Monte Carlo truth, which essentially verifies that our method is correct and it does match our industry standard today. And it is much faster. So that was our initial goal anyway, was to get fast and accurate results with analytical and semi-analytical methods. And that's what we have proven today, that that's what our method provides us with. So in conclusion, our method gives us very accurate results of probability of collision. And it is a faster and more accurate method than the Monte Carlo numerical propagation standard that we have in industry today. And that was the motivation and the method and the case study of my research. If you have any questions, please feel free to ask them now, or you can connect with me via LinkedIn or send me an email through my Colorado email as well. I was really excited to present to you guys today, and I hope I did a good job of it. If you guys have any questions, please feel free to ask them now.
So open up for questions. Thank you. It was wonderful. Any questions?
So is the method actually being used today?
Could you repeat that?
Is this method actually being used today?
No, the slower method that's more accurate is the one being used today. And this new method this has been developed over the last year. So this method has not gone to the industry yet. I did have an internship last summer at a company here in Boulder, and they wanted me to research the same methods, and I told them the solution I had, and they're actually starting to implement this now. So this is moving into the industry now. This is a very new method that has just been developed.
Thank you.
Yeah.
Christy? You're muted.
I know. I was just unmuting. Thank you very much, Yashika. And this question isn't directly related to your research, although you did a great job presenting it. Of course, a lot of it went over my head.
Yeah.
And I don't think I'm alone.
No.
Can you talk a little bit about STEM studies for women in India and what you're doing around that?
Yeah,
that effort?
definitely.
Good question.
Definitely. Especially space education is very lacking in India. And the number of women going into space education and STEM education has been rising over the last few years, but it's not still where it should be. So I've been working with an NGO actually for the last couple of years called VOA India. VOA is actually an international organization with a big chapter in the US as well. The India chapter just got set up about a year ago, and I was a part of it since the beginning. And that's what I've been working with. They're actually working on spreading space education in India, and then also providing, the title is actually Women of Aeronautics and Astronautics. So the goal is to get more women involved in space education, and then also give them more opportunities once they're in the education, once they are pursuing their undergrads or grad degrees. And they have done a lot over the last year, including organizing conferences, including sponsoring people to go to conferences, and organizing lots of these Zoom webinars with companies in India, with startups in India to give them job opportunities. And there's been a lot more that they have done over the last year. This semester in April, they're actually hosting their first Women in Space conference in India. And this is going to be the first initiative like this that's happening in India. And I'm working on that with them as well as the creative head for the advertising. So I think this organization can really make a difference. And in the future, I hope to work a lot more in this area as well. Thank you for the question.
Kay,
I think it's just, it must be astounding to have your research be beginning to grab hold and be used in the space industry. That has to be so exciting. And I'm wondering what's up for you next? Where are you? What do you want to do with this?
Yeah, so I didn't understand the impact that this would have on the industry until I went to the internship this last summer at Space Nav. And when this was the exact topic they wanted me to research and implement in their code, I was mind blown. Then this research will actually make an impact in the industry.
Huge.
And it's a pretty significant impact.
Yeah.
Because we'll know sooner when there are collisions occurring in space with less resources being used. So in future, I am continuing work in this area itself, but incorporating more real world dynamics. As I showed you the example of only the two-body problem where we only have Earth and a satellite being considered. Now we'll bring in solar radiation pressure and third body effects and the effect of Earth not being a perfect sphere and all of these dynamics and adding them into this method so that we can have more realistic applications of this. This is just like near term, and then long term, I would also want to see the impact of this maybe on asteroid research. So asteroids or natural celestial bodies rather than just satellites and just near Earth. And then after PhD, I hope to, professionally, I hope to go into the industry for a few years. I also hope to pursue space law at some point in the future and hopefully make a more global impact on the space industry as well.
Thank you. That's wonderful.
Yeah, thank you for the question.
Okay, any other questions? Okay, thank you again, Yashika. Before I introduce Jamie, our second AE fellow, I wanted to make sure everyone took a look at the chat for a way to donate to Amelia Earhart Fellowship. As you can tell, they greatly benefit and provide opportunities for women studying in aerospace. And so take a look at that opportunity to donate. And if you do donate, you will be in the chance for a drawing for a $25 gift card from Amazon. And that's on the compliments of Deb Beatty, our area director. Okay.
Just a quick thank you again. And it was an honor to present in front of you. And I hope that I continue seeing you guys over the next few years.
Oh, that'd be wonderful.
Thank you.
Thank you.
Congratulations.
Okay. All right. So Michelle, pull up the next slide for Jamie. All right. Jamie is also in the aerospace engineering at CU. Her study focuses on creating a computational model of human perception that incorporates visual, tactile, and vestibular cues for processing. She received her bachelor's degree in aerospace and engineering from MIT, and she enjoys outdoor activities such as hiking, cycling, and climbing. Her presentation name today is Measuring and Modeling Orientation Perception in Flight-like Scenarios. And the orientation perception is our understanding of our location and motion in space. Spatial disorientation is when your orientation perception is different from your true orientation. Spatial disorientation can very quickly become disastrous when piloting aircraft and spacecraft. By measuring orientation perception and modeling it, we can better understand and thus prevent episodes of spatial disorientation. So with that, take it away, Jamie.
All right, let me just share screen. All right, so as mentioned, my title is Measuring and Modeling Human Orientation Perception. We've already gone over the definitions, thank you so much, really quickly. So I'll very briefly run through them again. Spatial orientation perception is you, the human, your understanding of your location. So are you sitting on a chair? Are you sitting in a car? And are you moving? Are you moving forward? Are you accelerating? Are you rotating? Spatial disorientation, as noted, is when your spatial orientation perception is different from what's actually happening. An example of that scenario that you might have already experienced is when you're sitting on a train, you're sitting still at a platform, the train isn't moving. However, the train next to you starts moving forward and you see it through the window. Momentarily, you might have this false sensation of, oh my goodness, I'm moving, when actually you're not. That's a kind of benign and very small example of spatial disorientation. During flight, you can fly into a cloud and lose all your visual cues and very quickly become disoriented, far more so than that train example. Flying into a cloud especially is extremely dangerous because of spatial disorientation, notably in a fixed wing small aircraft, so kind of GA aircraft that you might take off from, say, at a local airport. Time to crash is on average less than 2 minutes. And for a rotor wing, so in a helicopter, a pilot that flies into a cloud or loses their visual cues, who doesn't have their instrument rating, is likely to crash after just 1 minute. Cognitive knowledge of orientation is something a bit newer. Cognitive knowledge of orientation refers to your knowledge of your position and orientation and motion in space as a result of every single cue available to you. So that includes instruments. So as a pilot, you have instruments like an attitude indicator, a roll tilt indicator, and an altimeter. These are all cues that give you information as to what your orientation is. Cognitive knowledge of orientation saliently differs from spatial orientation perception in that you are using generally your eyes and ears to read or hear information about your orientation that has come to you in the form of a natural language. So kind of you're reading, say, a 10 on the roll tilt indicator, you're not just kind of feeling your sensation of orientation of, oh, it feels like my head is tilted to the side. The kind of, it feels like my head is tilted to the side is spatial orientation perception. And kind of, I've read my tilt as 5 degrees precisely is cognitive knowledge of orientation. So before we get into the weeds of exactly what I'm doing, I'm just going to reiterate the motivation for it. So as noted, spatial disorientation is really, really bad. I'm happy to talk more about this offline, and there are far more sources. But generally, when you become disoriented in a flight scenario, it can very quickly become disastrous, and aviation mishaps, specifically crashes, tend to result in fatality of everyone involved, unfortunately. Therefore, it's pretty important to prevent spatial disorientation when we're flying. In order to do that, we must first understand why it happens. We can do this or understand why spatial disorientation happens by measuring orientation perception in flight-like scenarios. When we have measured orientation perception in enough flight-like scenarios, this should give us sufficient data to create a model of spatial orientation perception, which can then predict spatial orientation and when spatial disorientation occurs in scenarios that we can't actually measure in a lab. So for example, the lab we have at CU allows us to measure certain dynamic motions like rotations, tilts, and translations. What it can't do, though, is measure an orientation perception during a dynamic scenario like a death spiral. Those of you who are pilots, most of you, I imagine, are familiar with the death spiral maneuver, which is an unfortunate situation where a pilot in a fixed wing aircraft, their nose starts to pitch down and the plane starts to turn inwards. And if this happens in the dark, this is an unfortunate known failure mode where spatial disorientation takes over. And the pilot might not be aware from just their perceptual cues that the plane is spiraling downwards. This is an example of a known motion that causes spatial disorientation that we would not be able to measure in a lab. By modeling orientation perception, we hope to ultimately be able to identify more such dynamic motions. So death spiral is like a very well-known one, and we're able to train pilots to recognize it. We are hoping through my research to be able to figure out more motion profiles like this that we can then use in training and hopefully prevent or at least have the pilot recognize that they might be experiencing spatial disorientation. So for some background, again, I apologize that so many of you will be familiar with this already, but the vestibular system is what gives you your sense of balance. Shown on the right is a diagram of one such kind of full vestibular set of organs. You have one of these in each inner ear. The vestibular system, or like one part of it, or each half, consists of semicircular canals, which are these three guys here. I hope you can see my mouse. These are three approximately perpendicular semicircular canals. These guys transduce angular velocity. So these three semicircular canals are able to tell you whether or not you are rotating, and they give you a sense of what speed you're rotating at in the three different planes. You also have the otolith organs, which are the utricle and saccule, just here and here. Your otolith organs give you a sense of linear acceleration. That is linear acceleration in the X, Y, and Z directions. Notably, however, our vestibular system isn't perfect and wasn't designed for what we call unnatural or flight-like motions of sustained acceleration or sustained angular velocity. As such, what's important about this slide is that we have something called velocity storage and signal decay in the vestibular system. Signal decay is when you're spinning for a long period of time. If you've ever sat in an office chair and just kind of spun around and around and around with your eyes shut, eventually it becomes kind of difficult to tell like whether or not or how fast you're still spinning. That's because of a limitation of just the organs in our ears. And then when you stop spinning, it will all of a sudden feel like you're moving in the opposite direction. It's a very strange sensation. So that is what we call velocity storage, that kind of when you stop moving, your vestibular organs will be like, oh, whoa, we're moving in the opposite direction. We also are able to perceive motion and where we are in space through our eyes. Our eyes are obviously very complicated organs. So to simplify it and get right to what we want to take away here is our eyes are great. They can sense both angular and linear acceleration, both angular and linear velocity, and also position. Our eyes sense position by looking in the world around us and seeing landmarks like, say, the chair we're sitting on, or the table we're sitting by, or a window is over there, or buildings are in a certain location, give us cues as to where we are in space. And then something called optical flow gives us our sensation of motion through our eyes. So shown on the right is an image of like the world is coming past the viewer, which gives us sensation of moving forward. It's this visual flow around us, which tells us that we are moving and how our eyes sense our motion in space. We also have visual vertical and horizontal cues. So on the right, we can see a horizon that tilts a little bit as the GIF moves through it. That gives us that kind of horizon. It gives us a cue as to how much we are tilted. We call that a visual horizon. We also have a visual vertical cue, not shown in this image, but we know things like trees and buildings to be upright and perfectly vertical, which gives us a sensation of kind of which way up and down is and which way we should be feeling the sensation of gravity. I'm going to get right into literature review. So I would like to introduce a class of model called observer models. Observer models started in the kind of late 90s, like early 90s, kind of late 20th century. The one I've shown here was presented by Dr. Dan Murfeld, who is now at The Ohio State University and is still working. An observer model takes a dynamic scenario in and then outputs a prediction of what orientation perception is going to be. So in this model here, we've got angular velocity going in up over here and linear acceleration going in up over here. So this is our kind of dynamic scenario. It's how we're moving in space. These two types of motion are then passed through the model. I won't go into all the details. And then out the other side, we get omega hat, which is our predicted perception of angular velocity, our predicted perception of the direction of gravity, and our predicted perception of acceleration. This particular model shown here is vestibular only, so there are no other cues to talk about. And what's important about this model is that it contains internal models of sensory dynamics. So here we have an internal model of kind of our body dynamics and where we are in space. And then over here, we have an internal model of the limitations of our semicircular canals and otolith organs. So in the model, what's actually happening here is we have a transfer function that accounts for that signal decay and velocity storage that I mentioned on the previous slide. So this transfer function kind of acts like a filter that will, after a prolonged period of angular acceleration, that signal's going to slowly decay to zero. The other important part of this particular model is what we call sensory conflict. Sensory conflict in this situation does not refer to when your eyes tell you one thing, but your vestibular system tells you something else. Sensory conflict refers to a difference between the expectation of what our senses are going to give us and then what our senses actually give us. So here we have the motion profile going in, we have our model of body dynamics, our model of sensor dynamics, and then this is passed through like an internal brain model. So this is kind of a model of what's going on in our brain. Our brain then kind of reads that signal in, essentially puts it through the reverse process to then back out what we think our motion profile is. So our brain is like aware that our senses aren't perfect and is able to essentially apply a reverse model of body dynamics and then a reverse model of sensory dynamics. We then find the difference between these two, kind of what we are actually getting in from our senses and what we expected to get from our senses, which is then pushed back through the model this way. This model in particular was initially made for spider monkeys, but is relevant to humans. Next up is a 2009 model by Michael Newman. This model incorporates visual cues, and it is a huge step up from the initial Murphy model. Notably, however, that vestibular-only section is pretty much unchanged here. We have the addition of visual position, visual velocity, visual angular velocity, and visual G. Visual G is kind of our sensation of like which way is up. This model is pretty good in the sense that it includes gating and the ability to like turn visual cues on and off. So your vestibular cues, no matter what you do, like you're going to have them, you can't turn them off. Visual cues, you can close your eyes, you can fly into a cloud, you can cover your eyes, so you can lose those. Those can go on and off. This model will handle that. But a key limitation of this model is that while it can handle changing visual cues, we're aware that it's not accurate for them. And that is where my research kind of comes in. There are existing models of orientation perception. However, there are a lot of known failure modes of these models when we know that they're just wrong. So that kind of gives rise to the three separate aims of my PhD research. So the first aim is modeling orientation perception when someone flies into a cloud. So right now, based on existing literature review, we don't really know what happens to orientation perception in humans when we suddenly lose our visual cues or when we suddenly gain them. We are particularly interested in that kind of sudden visual transition scenario because it happens so often in flight and is so often associated with aviation mishaps. The second aim is to then update these existing models of orientation perception to be robust or to reflect the data that we've collected in the first aim. And then the last one, as noted, pilots are often flying with instruments. There are a lot of instrument-rated pilots out there, and we care about what happens to cognitive knowledge of orientation when you have an instrument. So aim 3 is set up as with during dynamic transition, so like when the instrument is suddenly available versus not available, rather than the instrument being available the whole time. For aim 3, I will get into precisely why I've set it up that way a little bit later. So for aim 1, I'm first going to go over the types of motions we are doing. Based on the motion devices we have available at CU Boulder, we're able to do earth vertical yaw motion. So kind of this black line up here is kind of our earth vertical going upwards. And then that green arrow should hopefully indicate like kind of it's just was spinning it around, kind of like you're spinning in an office chair, is one type of motion. We then also want to do roll tilt, which is shown by the blue arrows, kind of tilting from left to right. Roll tilt, we are generally going to do in conjunction with translation. Simple roll tilt, because of the changing gravity vector, is one difficult to do more than like 20-ish degrees in terms of the motion devices we have available. And then the addition of translation is going to make it a bit easier to generate dynamic motions, which typically or should result in spatial disorientation, because again, we are interested in measuring scenarios where disorientation is likely. We have opted not to include pitch tilt because based on past research, we imagine pitch and roll tilt to be pretty similar in how spatial disorientation occurs. I think there's going to be a key difference between spatial disorientation during yaw motion versus during roll motion. So this is a picture of how we are measuring orientation perception during yaw motion. I wasn't able to include a video, unfortunately, but here you can see a model that I have in one of our motion devices, which is a chair that is able to spin to a very high degree of accuracy. We can change the spin rate very easily. We want to put the subject in VR so that we have full control over what they can and can't see. Although you can't see it in the photograph, the subject also has 2 controllers in each hand where they have to press a button. They're tasked with pressing a button every time they feel like they're rotated 90 degrees. And they've got buttons in the left and right hands. So if they're rotating to the right, they press the right-handed button. And if they're rotating to the left, they press the left-handed button. This gives us a perception, this gives us the subject's angular position perception and also the angular velocity perception by simply integrating the angular position that we back out of that button press task. For this particular aim, I've got 6 different motion profiles and 4 different visual conditions. So the motion profiles are ranged to include some kind of well-known, this results in spatial disorientation style, yaw motion profile, and then yaw motion profiles, which are kind of all over the place in terms of angular velocity. The motion profiles have specifically been designed to confuse the subject. The 4 different visual situations are as shown. So we definitely want to measure orientation perception when the lights are on and when the lights are off. And then 3 and 4 are our kind of transition situations. So when the lights are off, like that VR headset is showing absolutely nothing. It's completely blank. There is like no light leak. It's completely dark. The subject sees nothing. And then for the yaw portion of the task, when the lights are on, the subject sees this kind of dot matrix display. They're kind of inside a giant wiffle ball, so that when they move, like these dots will move past them and give them that optical flow that I was talking about earlier. And then based on that optical flow, they should be able to get a sensation of motion, or like that visual motion cue. So before we get into preliminary results from aim 1, I want to go over a couple of definitions. So when I say lights on pattern, I'm referring to a lights on pattern of orientation perception. So certain motion profiles will have like an expected, this is likely what the subject's orientation perception is going to be. Generally, when the lights are on, we'd expect orientation perception to be consistent with the motion. So when the lights are on, humans are very good at perceiving that orientation. When the lights are off, we generally expect to see that signal decay. So we generally expect to see orientation perception kind of drop or trend towards 0, even if the subject is still moving. So when I say lights on pattern, I generally mean orientation perception that is consistent with the motion. When I say lights off pattern, I mean orientation perception that is slowly decaying. So this is a sample graph of one such motion profile. There's a lot going on here, so I'm going to take a minute to slowly walk us through it. So in black, we have the actual angular velocity. So this is the subject rotating, and it's how fast they're rotating in terms of degrees per second. And on the x-axis, we just have time. So this is a 2-minute long motion. where the subject starts rotating at 20 degrees and then bumps up to rotating at 50 degrees per second. And then at the end, the motion stops. In the shaded part, like that's the lighting condition. So at the beginning of this motion, the lights are on and then suddenly they turn off. In red, we have the subject's perception of their angular velocity. So over in red, we see that when the lights are on, that thick red line, kind of what our subjects are doing, is pretty consistent with the motion. There's a little bit of a delay because the task is like a button press every 90 degrees. We expect that. And then we see the red line kind of consistent with the motion until the lights are turned off, and we do start to see some of that signal decay that I've been talking about. The green line, which looks pretty similar to the red line at the beginning, is the same motion profile, but where the lights didn't change. Like the lights were on the whole time for the green line. And we see the green line, it tracks the motion profile pretty well for the whole 2 minutes, which is about what we'd expect. And then in the dashed lines, we see what the existing model, so that 2009 kind of colorful block diagram model I showed you, this is the prediction of orientation perception based on that model. So the dashed line in red we see is pretty different from our data, and the dashed line in green we see is pretty consistent with our data, which is great. And what we'd expect. So the model's pretty good for the lights on scenario. However, we see a pretty big divergence for the lights, kind of when the lights suddenly change. So like when we begin, we see orientation perception following the lights off pattern. We then see a transition period of several seconds, that red line dropping. And then we don't quite see the red line following a lights off pattern, which is what we'd expect, but more on that later. Here is some more data again from your. So again, on the left, we have the same, I apologize, it's so complicated, the same color scheme as we just talked through. And then on the right, we kind of have the opposite where the lights start off and then go to on. So when the lights suddenly turn on, we expect to see something happen. To real quick walk through it, it's the same setup where the dashed line is the model prediction and the solid lines are what the data we got from our subjects. And again, that black line is the true motion profile. So the blue line, the kind of dark blue line, that's lights off. That was kind of chosen as a dark blue to be consistent with no lights at all. And then the orange line is the measure orientation perception we got when the light suddenly turned on. So when the lights went from this gray block off to this light block on, that orange line is what we are seeing. To get a better look at the data, let's real quick remove those legends so that we can see everything. There's a lot going on. Now that we kind of talk through what it means, again, we see here, we see our red and green lines pretty consistent where the lights are on. And then we see some decay when the lights go off, and then a big amount of, this is that velocity storage I was talking about. When the lights are off, you've been moving for a while, and then suddenly you stop moving, it starts to feel like you're moving in the opposite direction, which is about what we'd expect to see. But again, the model doesn't really match that. Over on the right, this is kind of where we see something we didn't really expect to see. So in the dark, we'd expect to see a lot more of that signal decay I was talking about, but we see both the blue and orange line track the motion pretty well. It's possible that because this motion was very simple, this was a simple step and so consistent that subjects were able to estimate, like, I'm probably just moving at the same speed. However, we do see that kind of bump up when the lights suddenly turn on in the orange line. But again, we don't see the model kind of matching any of the data here, which is not ideal. And again, this is like pre the model being updated. This is like the model as it is before we've done any work on it. That is it for preliminary results for AIM-1. We aim to collect quite a bit more data before publishing our findings from this. But I think the main takeaway here is that during a visual transition or in a period where like visual cues are suddenly appearing or disappearing, we initially see in the kind of lights on to off scenario, a lights on pattern of orientation followed by a lights off pattern of orientation, and then a transition period that is pretty smooth and several seconds long. And then in the opposite scenario, we see something a bit different. We'd expect to see a lights off pattern of orientation going to a lights on pattern of orientation. So we see that orange line tracking the motion really, really well, while the blue line does not when the lights turn on. And then again, we see that same kind of transition period of a few seconds as the lights go from off to on. So it's kind of the same lights off pattern, transition period, lights on pattern of orientation perception. So that's kind of the aim of what we want our model to look like when we start to update it. So for aim 1, we also have role. So we're doing the yaw portion of the study and then the roll portion of the study. So role, we're using a different motion device. Here we're using something called the tilt translation sled. So over on the right is a picture of the chair that the subject will sit in. And here we've got our crash test dummy. The subject again will be in VR, so we can control everything that they see. And instead of using a button press task, the task here is just to hold a bar horizontal as they move through space. I expect to use about 12 motion profiles with those same 4 visual conditions. So here is a picture of the haptic bar that the subject has to hold onto. So this is kind of, there is no subject in the chair, so we can get a good view of the bar here, but this is kind of over the shoulder of someone who would be sitting here. So this is kind of like, this up here is the headrest, this is the seat, and then the subject would hold onto the bar here and here. And as the chair rolls, they have to hold that bar flat, which is how we get our, which is kind of how we read our data from the subject. We want to know what their roll tilt position perception is. They will also be tasked with giving verbal reports. So not on the, sorry, that is a different study. This one is just the haptic bar for now. Oof. Once we collect data for roll, I will have more to give you. We don't have that right now. So I'm going to go into aim 2. So aim 2 is likely going to be making changes to this particular model. I did not include a graph. So as noted, the model is one, not completely accurate for the scenarios we measured, particularly as we saw with like the aim 1 yaw data. And a second issue with this model is the data shown in aim 1 yaw had to be smooth. There are a lot of spikes and discontinuities in the output of this model as it stands when we change the visual cues, which shouldn't be there and we know don't happen. So right now I'm experimenting with adding filtering to the model. So right now kind of visual cues go in here, 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 and here. If we have a sudden step in the visual response, all of a sudden this model gets a ton of new data, which results in a huge spike. In order to prevent that spike, I am hypothesizing that there is filtering going on in your brain at either locations A or B. So filtering at location A would indicate that when you are moving and you suddenly open your eyes and get all these motion cues, this is your brain saying, oh, like, wait a minute, we suddenly got information that disagrees with what's happening already. I'm slowly going to integrate this before I fully trust the cue that's going in. So this is kind of the cognitive side of what adding a low pass filter to location A or location B will do. What it will do to the model is essentially result in a much smoother transition when visual cues are suddenly turned on. Another possibility that we are looking at is dynamic reweighting of cues. So right now, visual angular velocity cues go in here through this orange block and they pass through this part of the model and it integrated at this blue gate here, where we get additions from vestibular cues from the otolith organs coming in here, the semicircular canals, and then the eyes, which ultimately go into our perception of angular motion here, this omega hat. A difference that could be made is reweighting those cues. So right now, these cues are added and they're all weighted equally. One thing that we are thinking about doing, which is quite similar to Kalman filtering, is here we have a nice little error term, which tells us how different our visual information is from what we expect our visual information to be. We could change the weighting over here based on the size of that error cue. So if that error cue is huge, that means like you don't think you're moving and then all of a sudden you open your eyes and the world is rushing past you, that error cue is going to be very big. If that error cue is big, we then kind of want to give less weight to that information because it's not what we expected. This is another possibility of how we'd get the model to match up to our data. It's very possible that both types of models, this kind of adding filters to locations A and B, or this dynamic reweighting, both will work. And we're pretty curious to see if one works better or if both work just as well. Here are just some preliminary results. I apologize for not having shown this graph earlier, but to illustrate kind of where this model majorly is falling short, even if our data isn't finalized, is in red is a sample input motion. So it's angular velocity. We're kind of rotating at several different degrees per second. The motion's pretty dynamic. The lights obviously change. In yellow is what the observer model predicts right now. We see this massive sudden spike up to 200 degrees per second. And we're very much aware that even if you are disoriented, it's highly unlikely that when the lights suddenly turn on, you'll like perceive yourself to be rotating like 5 times faster than you actually are. We're pretty sure that this is just an error in kind of what's going on in the model. And this huge spike is definitely not something we see in any of our experimental data so far. Right now, I've added a filter to position A, so just this little green filter here to the model. And we've already got a much smoother curve in purple shown below. And this is like a baseline filter. I haven't tuned it. I haven't changed the gain. It's just got a time constant of 1 and a gain of 1. And we're able to remove this massive spike, but we still see this nice discontinuity of, we have a, sorry, not nice discontinuity. This sudden jump up, we have our transition period here as we go from light to dark, where we see the signal decay. The model predicts that when the lights suddenly turn on, the human will be like, oh, right, no, wait, I am moving, I am rotating. A caveat here is that based on data from that I showed earlier, we would expect this purple line to jump all the way up to the red motion a bit faster. And it actually doesn't even do that until right at the end of the motion. So while the filter removes the discontinuity, I still definitely have a lot more work to do in terms of either filter tuning or looking at other ways of getting this purple line to be a bit more consistent with the data that we have collected already. So AIM-3 is basically looking at AIM-1, but with an instrument. So measuring cognitive knowledge of orientation, information that you can just read off a roll tilt indicator. Here, I've chosen just to use a roll tilt indicator because to my knowledge, this is the first time someone has tried to study what happens to your knowledge of orientation perception under the influence of an instrument. So we definitely want to start with just one instrument and not the full 6-pack. I've chosen a roll tilt indicator because this is generally most salient, like roll tilt as opposed to a yaw tilt indicator, because this is like a very well used and quite important flight instrument, particularly when it comes to spatial disorientation scenarios. A attitude indicator definitely is as well, but I did want this arm of the study to match up the kind of the roll tilt in the first arm of my PhD. The roll tilt indicator in this particular part of the study is going to suddenly appear and disappear to simulate a pilot needing to kind of look at the instrument and then look away. Like realistically, a pilot's never going to be staring at just one instrument the entire time. In order for this experiment to control precisely when the instrument is looked at by the subject, we are just going to make it appear and disappear so that every single subject gets to look at the instrument at the same time. So again, it's appearing and disappearing because pilots don't stare at one instrument the whole time. So AIM-3 methods is going to use very similar equipment to what was shown in AIM-1. We're using the tilt translation sled, which again is a big device that can translate and tilt. In this particular setup, we are not going to have the subject in VR. Instead, so again, this is a view over the shoulder of the subject. There's no subject sitting in the chair so that you can still see all of the things. Here, we're going to have a screen-mounted display, which is going to give the subject an accurate reading of their roll tilt when the roll tilt indicator is displayed. And again, the subject is going to use a haptic bar to report their sensation of roll tilt. A difference here is that subjects are going to do every motion multiple times because we want both a haptic bar report. So the haptic bar is just kind of a very intuitive hold the bar steady task, which gives us a indicator of their perception of orientation. Subjects are then going to have a verbal report task. This is not going to be done at the same time. It's going to be done on a different day or a different trial, as we call it. Subjects will be asked to verbally report their estimated angle of roll tilt in order to give us a reading of their cognitive knowledge of orientation. So that is subjects are going to hear an auditory beep, and then we'll have to read out like 5 degrees to the left, 10 degrees to the right, to the best degree of accuracy that they can, their perceived roll tilt. They may or may not have the roll tilt indicator at the time of the beep. We are aiming to have some beeps, they have the roll tilt indicator, and so the subject should just be able to read it off the indicator, and at other times they won't. So that's kind of just simulate a scenario where a pilot's trying to think about what their roll tilt is in order to control the plane, both while they are looking directly at the instrument and while they are not able to fixate on that one instrument. So that is it for in terms of what I'm trying to do for my PhD. I would love to acknowledge certainly the Office of Naval Research, which is funding this project as like part of a much larger multi-university initiative. So I would love to thank the Amelia Earhart Fellowship, without which I would not be here. And of course, the Bioastronautics Laboratory at CU Boulder and all the equipment that I am able to have access to. Obviously, this PhD would not be possible without access to a lot of different motion devices. So with that, thank you so much, and I would love to take questions.
Thank you so much, Jamie. I actually kind of understood that presentation, which is not always the case with our Amelia Earhart Fellows. I have a question. The first thing that came in my mind is, how did you decide that this is what you wanted to study, and are you a pilot?
So yes, I'm not current right now. I have a recreational pilot certificate recognized in Australia, which is my home country. Unfortunately, I've not gotten around to having it transferred here because it's quite expensive. I do like flying. I'm obsessed with human spaceflight. I'm very excited about space travel, flight involving humans, hence ending up in the Bioastronautics Laboratory. I ended up on this particular project because it obviously concerns human flight, although it's not human space flight. I was very excited about the computational modeling part. Like, I love working with people. I definitely love that my research involves human subjects. It's like really nice to meet the people that you're testing, who are generally pretty keen and interested in space as well. But it's also nice to, like, often when we do human subject research, it's a lot of statistics. Kind of you're measuring something about the subject and you're kind of comparing populations. I was really excited about this project in particular because we do a little bit of stats, but then it's a lot of this kind of, we're making a nice model to predict something out of it, which is not something you always get with human subject testing. There is a question in the chat from Pamela. What criteria do you use in selecting your subjects? Generally, we are just looking for healthy adults between the ages of 18 and 55. Sometimes it's a bit narrower. Sometimes it's like 30 and 55. Because astronaut and pilot populations tend to be older than 30. Overall, though, we are just looking for people who are healthy, have a functioning vestibular system, like don't have a history of falling, and are obviously not colorblind. So anything that would qualify you to be a private pilot would be ideal. Like if someone's a pilot, we definitely want to test them, but it's often not realistic to be able to find enough subjects who have a pilot's license to test them. Do you have another question?
Pam?
Yeah.
There we go. Yeah, my husband is a pilot and he would have absolutely like been mesmerized listening to you because he talks about this challenge a lot. If you did test pilots, and I'm sure you differentiate the data when you report it, do you find that pilots are testing differently than those that are not pilots?
So we definitely hypothesized that pilots would test differently. Unfortunately, I think like one of the subjects so far was a pilot, and just with one subject, it's not a big enough subject pool for me to be able to be like, definitely. Almost certainly there'll be a difference, but I just don't have the data to say it. I wish I did.
Pam, you should volunteer your husband.
Yeah.
He'd sign up tomorrow, but he's over 50 or whatever you said the cutoff was. Too late.
Catherine?
I'm muted.
Trying to unmute. Thank you for your presentation. Like Michelle, I think I understood like 75%, which is better, which is pretty good for me. as an educator. I do know a pilot that's 44 years old and
Okay.
he lives here. If he's interested, how would I get your information to Jeff?
Do you have my email?
Yes, I do.
If you have my email, just shoot me an email and CC your pilot friend.
Okay, that would be great. I have his
That would
phone
be-
number.
Yeah, that would be the easiest way to do it.
Okay, great.
Yeah, I thought about that too. The other experience, so I'm not a pilot, but when you started your presentation and you were explaining the difference between what your eyes and your senses are telling you and how you actually feel, I think the other way that maybe some of us have been able to experience that is scuba diving or being underwater. Because I know that I found it incredibly disorienting to, as you were saying, the difference between like what's up and down. And so it was just fascinating. It's not really a question, but I assume that there are
if any
very,
of you,
very similar things happening there.
if any of you are divers and have done like a night dive and turned off your torches, which perhaps you shouldn't have done, then you'll probably know how, or shut your eyes while diving. You'll probably know how quickly you lose sensation of like which way is up.
By the way, Jamie, the friend I know has a PhD in physics.
Oh,
So,
fantastic.
he might be interested in this research.
Any other questions?
I have a comment. I was just thinking in terms of potential candidates to test, does the university have a gymnastics program?
I assume so.
So gymnasts have to have good spatial relations and understand what their bodies are doing.
Oh, yeah.
Anyway, food for thought for potential candidates.
Yeah.
Because, I mean, they're very aware of what they're doing because they need to get their body to do certain roles exactly. So
Yeah.
I think it would be a really cool candidate to test.
Yeah, and probably a criteria we should include. So like when we test people, we have a questionnaire of like, are you a pilot? Do you have flight experience? We should probably include that. So we know if that's like a confounding factor or something that might change our data or cause an outlier.
Dawn, I think that's a really good point, because it also, like dancers, they do what is called spotting. So they know where they are when they're turning. Their head has to come back to the same spot every time. So I understand what you're saying.
And Dawn and Michelle, I would capitalize on that when it comes to CU. What about our skiers? And, you know, the extreme sports that go on with, you know, people up in the air doing this and then actually landing. Yeah, it's very fascinating. Thank you.
Okay, any other questions for Jamie? Okay, we really appreciate both of your presentations. We are now going to move to the award ceremony. If we were doing this face to face, I'd be having you up in front of everybody and handing you an actual certificate and your wings, which are a pin. So with that, go to our virtual award ceremony. I'd like to present to Yashika her virtual certificate, and then you see a picture of what your wings will look like. And the next slide is to Jamie, to award Jamie her certificate, and then a picture of your wings. I will be mailing these to you. I'll confirm your home addresses, but you will get your certificate and the wings in the mail. So with that, everyone clap virtually in honor of our fellows.
Where's the
All
other
right.
fellow's certificate?
Sorry.
Where's the other fellow's certificate? Oh, there. Okay. We didn't see it.
So show you she. There you go. There you go. All right. Okay. With that, I'm going to turn it back over to Deb Bain.
Thank you so much, everybody. I appreciate. Can you hear me? Okay, thank you so much, everybody. I appreciate the fact that you those presentations are always so inspiring and I'm just so overwhelmed with how I'm sorry, so how smart you are. I mean, it's just crazy. Thank you so much for sharing your presentations with us today. Thank you for taking advantage of the Zonta Fellowship. We are so blessed to have your participation with us, and thank you again. I just want to ask everybody, please follow the link, donate to the Amelia Earhart Foundation. You have a chance to do it today. Everybody who donates to the Amelia Earhart Foundation today in conjunction with this meeting and this presentation will be entered in a drawing and will receive a gift certificate from me personally and from the area. With that, anybody have any questions, comments, concerns about or any further?
I see Catherine Maydell has a question.
Deb, I would especially like to thank, as president of Zonta Foothills, I would especially like to thank Michelle for being a wonderful host for this meeting. And she is our IT person, along with Pam and Marta. And we have so many people in our club that have expertise in technology. And I just want to really thank all of them I want to thank all of our Zonta Foothills members in being here, and all of you that have attended this meeting. It's always special. And we can host this meeting because virtually and in person at CU, which we have hosted at CU many years, and it's a great venue. And I want to thank Michelle for arranging that in-person venue many years. And so thank you all Foothill members that have attended. Thank you all across District 12 that have attended. And thank you, Marcy, for all your work in the Amelia Earhart field of being the chairman of this. And thank you for the recipients. We are very proud of you. Although we don't understand everything you said today, we know that it's very relevant, and we thank you for your research, and we wish you the very best in your endeavors in your career. Thank you for being here, everyone.